So we're going to use the same idea here where we're going to use the sine ratio as a length and then apply it to a unit circle. So I've got a circle radius 5 and I'm just going to, this isn't going to be the scale, but I have got a sine ratio of 0.279. Okay, so that means that that's 1. I'm going to zoom in a bit. And this length here is going to be, cosine of theta, and that is going to be sine theta, which is 0.279. So I know that the vertical distance here is 0.279, okay? And that's a radius 1 circle. That's how we define a unit circle, and the lengths in a unit circle are going to be cos along the horizontal, sine along the vertical. Now, that's not the only place, I think. Doesn't tell me the quadrant, so I actually have to put it into 2 positions. Now, I'm going to just, again, I'm not talking about a radius 1, I'm talking about radius 5, but I'm just going to start with radius 1 and use scaling to get to the radius 5, because I know that that triangle is 5 times bigger. So if I want to find out the coordinates of that point, I'm just going to multiply that by 5. So 5 times 0.279. That becomes my y coordinate of that point P. Okay, so that's going to be the y coordinate, and I can do the same thing here. Right? I can just extend that out to radius 5. Okay, so that's going to be radius 5 here. And then the y coordinate is going to be, again, the same thing, 5 times the original unit circle point. And I could establish those coordinates like that and work out those positions on the radius 5 circle by just using that unit circle as a unit rate and scaling it up or down. So working that value out, 5 times 0.279, that gives me 1.395, I think. Okay, now I can work out the distance here by using Pythagoras on the big triangle or the small triangle. I'm going to do it on the small one. I'm going to say that the cos squared value is equal to Pythagoras 1 squared minus 0.279 squared. So I get cos squared is 1 minus 0.279 squared. That's 0.922, so I'm going to square root that value, and I get a cosine value, which is my x position, as 0.960. Okay, so that's going to be, I'm going to zoom in a bit, 0.960. Okay, and then I'm going to multiply that value by 5 to get my x position. So I get an x position of 4.80. Okay, so that's going to give me 4.80 on the x position. And if I look at the symmetry of this, I'm going to get negative 4.80 on this side. So that's giving me those points on the circle of radius 5. And again, the idea is I'm taking that unit circle and using it as a unit rate to find positions on a bigger circle. So the next one here, I'm looking at a generalized point, MN, and it's on a unit circle. So if I'm going to generalize a point, it's probably easiest to put it into quadrant 1, although it doesn't have to be. It could be anywhere. The one thing you don't want to do is put it at 45 degrees. Okay, because 45 degrees implies some symmetry, and if we imply symmetry, we're implying some property that may or may not exist. Okay, so we're going to generalize it so it's not 45 degrees, and we're going to put that point there. So point is at there, and it's on a unit circle. And it says determine the value of sine and secant. Okay, well, if that's theta, that's a unit circle. This is how we've defined a unit circle. The x position, m, is cosine of the angle. The y position, n, is the sine of the angle. They are equivalent. Okay, so if we want to find out the value of sine, we can just say sine theta equals n. There's our answer. I want to know secant. Well, secant is the reciprocal of cos. Well, I don't need to do any calculations. I can just take the reciprocal of the m and say that that is my secant ratio. Okay, so this is a nice thing about unit circles, is that we can then now use those lengths, those positions, m and n, as ratios.